Good evening again, President IESL Engineer Arjuna Manamperi, President-elect IESL Engineer Dr. Kamal Laksiri, Council members, fellow members, other Chartered Engineers, Associate members, and other members of IESL, and ladies and gentlemen. I am Samantha Gunawardana. I am the chairman of the Building Services Engineering Sectional Committee for the session 21-22. And on behalf of the organizing committee, I warmly welcome you all for this webinar. And this is the first webinar of the series of webinars to come this year, organized by Building Services Engineering Sectional Committee of IESL, session 21-22. Among many activities we do in a session, webinars are one of them, and generally the invitation are open for general public. And today I see nearly 200 registered participants, and now we can see the numbers are more than 100. So I hope numbers will improve as we go on. Just a bit about the sectional committee. As you all have seen in the video, we have won gold awards throughout as the best sectional committee of IESL, and among other sectional committees of various other engineering disciplines. And the building services engineering is basically generally known as, we are in the MEP sector or M&E sector. We work along with building services engineers. The BSc charter route was first recognized in year 2010. And currently we have nearly 100 chartered engineers in this sector, and numbers are growing. And we have a directory of building services engineer. Again, the numbers are nearly 300, and we are a committee where civil, electrical, mechanical, engineering disciplines are in. Yeah, it's tough time when a webinar activity is organized. I'm sure there are many people behind the scene who are working towards success of this event. I'm sure they will do their best to make you comfortable during next 1 to 1.5 hours. I am sure also our prominent lecturer today, Engineer Pathum Jayawardena, will make this session a fruitful one. So thank you very much once again, and thank you very much for the organizing committee. I leave the floor to organizing committee to lead the next 1.5 hours. Thank you very much.
Thank you very much, Engineer Samantha. Good evening, ladies and gentlemen. I'm Kaushal Patrina from the Building Service Engineering Sectional Committee. I warmly welcome you all to the very first webinar organized by the Building Service Engineering Sectional Committee for the session 2021-22. Today's webinar will be a very exciting one, and the topic is transient voltage protection and the use of surge protection devices. Well, we all love our expensive electronic devices, and they play a considerable part of our lives in this modern world. So the protection of these is a must, and it is important, isn't it? Adverse effects caused by transient voltages might lead to disruptions, loss of revenue generation, service outages, equipment damages, equipment lifetime reductions, and downtimes. These can cost a significant amount to any kind of business to reduce its productivity, sales, customer confidence, and the competition. Then how can we overcome these challenges? Selection of proper surge protection devices are vital, and the selection must be done correctly with time assessment are in place. So today's objective of the webinar is to provide an introduction to these technologies, especially in modern building context. Thank you all for joining with us, and let me introduce our speaker today. Engineer Pathum Jayawardena was graduated from Department of Electrical Engineering, University of Moratuwa, and a chartered electrical engineer. He runs his own consultancy firm and has undertaken many prestigious projects both locally and internationally. Engineer Pathum is well experienced and carries a great exposure in electrical engineering fields. His expertise in design and consultancy can be seen in many landmark projects, including star-class hotels, factories, hospitals, and office complexes. Engineer Pathum has also obtained his MBA from Cardiff University, UK. He also shares his knowledge as a visiting lecturer for many institutes such as IESL, CITRAC, SIDA, SLIT, and many other institutes. Further, he has served as a resource person for several professional forums as well. Having ties and collaborated with many professionals in the field, Engineer Pathum has a wide vision to expand the building service industry for a safer and efficient Sri Lanka. Well, ladies and gentlemen, without any further excitement, please join with me to welcome our speaker tonight, Engineer Pathum Jayawardena. And one more thing, I would like to remind you that there will be a Q&A session at the end of the presentation. You can post all your questions to the moderator by selecting the moderator in the chat box. We will direct all your questions to the speaker at the end of the presentation. Well, let's move on to the presentation. Over to you, Engineer Pathum. Thank you.
Yes. Good evening, everybody. And thank you very much for the introduction. And I hope you all can hear me as well as my voice is clear and everybody can hear me well. So hope you can hear me, right?
Yes, Engineer Pathum.
Yeah, okay. Okay, then I'll share my presentation. Can you see the presentation?
Yes, we can see it, Engineer Pathum.
Yeah, okay. So actually, all the participants for this webinar organized by Building Services Sectional Committee are engineers. You all have very good technical knowledge, sound technical background, and I hope that all of you have better experience as well in this electrical and building services engineering field. So my objective here is to share my knowledge which I have gained through last 15 to 18 years working as an electrical engineer in the electrical field, and I want to put the theoretical stuffs and practical aspects in order for you to understand easily about this subject. Therefore, I would like to call this a technical discussion rather than a lecture and a knowledge sharing session. And with that small note, so I will move on to the presentation. So today I'm going to discuss with you these areas regarding the transient voltage and use of surge protection. First, I will give you an introduction about transient voltage, what it is. And then I will explain you why we need to control, why we need a device to control transient voltage, or why we need a surge protection device, in other words, right? Then let's have a look how these transient voltages can be happen in the electrical system, in the electrical equipment. And then as designers, as engineering practitioners in the industry, we always follow engineering standards. We can't do anything on ad hoc manners according to our personal experiences and this thing. Therefore, we have to follow always, we have to refer always a published engineering standard, right? So then I will discuss with you briefly, not very in detail due to the time limitations and all, what are the applicable standards for these transient voltage and surge protection devices. Then after that, I would like to discuss with you what are the technologies, what are the different types of surge protection devices available in the market. Then after that, let's discuss how we can select a surge protection device for a building to protect our electrical devices. Where to put, how to put, what are the parameters to be considered, those types of things, let's discuss, right? Then after that, I will show you some better practices of installation of surge protection devices. What are the mistakes, common mistakes that we need to do, we are doing in the industry, and how we can minimize those things to have a better electrical system, right? So let's move on. Then let's try to understand what is transient voltage, right? Actually, if you take voltage waveform, AC voltage waveform, it's a sinusoidal waveform. In ideal case, this waveform is uniform, but due to certain reasons, there can be sudden increase in voltage in the voltage waveform. But this voltage, sudden increase of voltage, or in other words, voltage spikes, won't last for long, right? It will be last only for a very short time, like 1 to 30 milliseconds. And the voltage amplitude in certain case go up to 1000 volt range. And in certain cases, it can go up to 100,000 voltage range depending on the reason for the voltage spike or transient voltage, right? Now here you can see in this voltage waveform, here you can see in this voltage waveform, there are some spikes in the voltage waveform, but it's for a very short period, right? Here you can see few spikes, not one, few spikes, right? So these transient voltages are actually really unwanted, unuseful. So this temporary voltage spikes occurring in the electrical system, therefore has to be cancelled out or limit by a device to have a better, a reliable electrical system, right? So then let's try to understand what are the consequences, what are the damages, and what are the equipment can be damaged due to this voltage spikes, right? So circuit breakers in the electrical system can be damaged due to transient voltages or voltage spikes. And control devices in the panel board easily can be damaged due to this transient voltages. Then lights, especially nowadays we are using LED lights, right? So I think you would have experienced very well. These LED lights are burned out, damaged due to this transient voltage. Then computers, especially the network devices, network switches, and also very commonly CCTV equipment can be damaged. Now here you can see in these images what I have shown here, right? Then electrical power receiving point, meters, circuit breakers are completely damaged due to this transient voltage. Transient voltages are, as I told you, there are various reasons. Let's look at what are the reasons for that. And certain reasons of transient voltages are highly dangerous. Now you can see here in the second image, electrical panel. It is completely burned out. And you can see here, this is a power supply unit of a computer, which also damaged, right, due to transient voltages. And here you can see electronic device, PCB, right? It is damaged, not the entire thing, certain component of the PCB is damaged. So this is also one of the reasons happen due to transient voltages, right? So therefore, transient voltages make a lot of damage, as explained in the introduction also. So it has a lot of adverse effect, and there are a lot of financial damages, and more than that, service outages and those kind of things also happen. So sometimes certain damages are millions, right? Therefore, we need a mechanism to limit this transient voltages. Let's move on. So then, let's try to understand why we need a surge protection device in our electrical system, right? In a good electrical system, there must be a device. Now, you know that in our electrical system, if there is a overcurrent in the system, we have overcurrent protecting device, MCB, MCCBs. If there is a short circuit in the electrical system, we have again a circuit breaker, MCB or MCCB, ACB, to cut off the short circuit in the electrical system. Then if there is earth leakage or earth fault, there are protection devices to cut off. Same way, we need a protection device to minimize or reduce or cut off the transient voltages, right? The device what we use to minimize or cut off or eliminate the transient voltage is called surge protection device. In easy terms, we call it SPT. Right? All of you have heard SPT. So in most of our electrical systems nowadays, we have SPT. Right? What it does, it limits the amplitude of the over voltage. It limits the amplitude of the over voltage to a not hazardous level, right? It limits to a not hazardous level. Sometimes not bring down it to zero, not hazardous level. Later in our discussion, let's try to understand what is hazardous and what is not hazardous, right? Throughout the system, throughout the electrical system, this hazardous voltage is not equal, right? In certain places, certain sections, hazardous voltage is a certain value, right? Now, if you look at our electrical system, I hope I'm audible well, right, to you?
Yes, Engineer Patum.
Yes, okay. So thank you, Sam. So then, actually, our electrical system, we have transformers in normal building services application, electrical system in a building, if you take a hotel or whatever hospital, right? We have a transformer, then we have MSB level, right? Then we have SDB level. In SDB level, we have several distribution boards, right? More than one SDB level. Then after that, we have final distribution board. So many final distribution board depending on the complexity of the electrical system, right? So then after that, we have lot of terminal equipment connected to this final distribution board. Our normal electrical system, irrespective of the size of the electrical system, it's generally like this. So then the hazardous voltage level at this point, right? At this point is a certain Sorry, there was an interruption. I don't know.
Now we can hear you, Engineer Patum. Yes.
Yeah, there was an interruption. I don't know. It's from whether it's from my end or anyway.
Now
So let's continue.
audible and visible. You can continue, Engineer Patum.
Yeah. So let's continue from there. There are two methods that SPD used to reduce the amplitude of voltage or voltage to an unhazardous level. That is common mode. In common mode, now if you take a electrical circuit, it's like this. We have a load, then we have a earthing point here. This is live, this is neutral. In common mode, what it does, it discharges to live and earth or neutral and earth. Right? In differential mode, there is another mode called differential mode. Differential mode, it discharges between the phases or phase and neutral. Right? That is how it works. So then surge protection devices are called in certain other names as well, right? Sometimes surge protection devices, the device has the same function called spike suppressor, right? You will see these things in different places, different technical literatures, catalog as spike suppressor, sometimes surge suppressor, sometimes surge diverter, right? The most common and very popular term is surge protection device, SPD, and sometimes transient voltage surge suppressor, right? TVSS also we call and also used to identify the same device, surge protection device. So same surge protection devices also in different shapes, different physical size, different arrangement, right? Let's look at later down the discussion, why it's different, how it differs, and what are the reasons behind for these changes and other things. Right. Then let's try to understand what are the reasons behind this transient voltage in the electrical system, right? There are two reasons. First one is internal sources. Internal sources means the electrical sources, electrical component within the electrical system creates voltage spikes, voltage surges, right? So, and there are external sources, external factors which leads to generate or which leads to occur voltage transients. Those are called external sources. Under internal sources, first reason is switching of electrical load, switching surges. When we switch on, switch off breaker or electrical switch, at that time, voltage surges can be happen, right? So at different level of the electrical system. And also there are magnetic inductive coupling. In magnetic inductive coupling, also magnetic inductive coupling also another reason for transient voltages. And also there is another reason, that is static electricity discharge. In our electrical system, static electricity is a very common thing. So when electrical static is discharged, there can be voltage surges. Let's look at in detail later how it happens, why, and why it happens. So then the external sources, under external source, first thing is direct lightning. So lightning is a very dangerous or very serious natural phenomena which cause voltage surges, right? Lightings also can be divided into two parts. One is internal or direct lightning, and the other one is indirect lightning. Now here in this image, you can see this is a direct lightning strike to the structure, right? If this structure is not covered or protected by a lightning protection system, a direct lightning can hit to the building structure and it will discharge through the building structure. So what are the electrical components inside the inside this structure can be damaged due to high voltages or transient voltages that can be happen at the time when this high power of electricity or electric current discharged through the building structure which occurred due to direct light, right? Sometimes voltage surges can happen due to indirect lightning. So every building, every structure nowadays connected with a lot of external sources. There are power lines connected to the building from outside. There are communication lines connected to the building from outside. There are water lines, metal conductive water lines. There are fire lines connected to the building from outside. So if a lightning hit on one of these lines, which is connected to the building, even far, the high energy can be transmitted through this line to the building. So then whatever the electrical component inside the building can be damaged due to this indirect lightning, which is transferred through the external connections to the building. And also sometimes this indirect lightning can hit to another place, not directly to one of these lines, right? Due to very powerful magnetic field, there can be inducers into the line, and this induced voltage can transfer again to the building and it can damage the electrical system, right? If you look at this table here, so out of number of lightning strikes coming to the world per annum, right? There are thousands of heavy lightning strikes happen in the world, in different parts in the world, right? Throughout the year, out of which 95% of lightning strikes are not really dangerous. It's about peak current is about 5 kiloampere. 50% of them is bit dangerous, high, about 35 kiloampere. Then about 5% has a very high peak current, it's about 100 kiloampere, and 1% it's about 200. So now you can see these external sources creates very high impact for the transient voltages because it generates huge amount of current, right? So now let's try to see what are these different reasons for the transient voltage. First one, switching operation, right? Switching transients occur in power system each time sudden and unexpected circuit changes occurs. So when we operate the circuit breaker suddenly, or when we operate the switching devices suddenly in the electrical system, a transient voltages can happen. How it can happen? When a motor connected to the electrical system, the mechanical power is stored in the rotating part and the electrical power is stored in the stator, creates high voltage spikes at the time when it operates, right? So now you can see here, when a circuit breaker close, there can be surges, right? There can be voltage surge, but it won't last for long. It lasts only for a few milliseconds and come down to the normal level. And when you switch off a circuit breaker, when you open a circuit breaker, also at the time when current reach to the zero level, right, there can be voltage spikes. It because at the time when current reach to zero, there can be huge arc in between the terminals and it creates this voltage surge. So then switching operation is one of the reasons it happens within the system to create transient voltages, so voltage spikes. All right. So then the next reason is magnetic and inductive coupling. This phenomena happens mostly in the electronic circuits, right? So when the energy coupled from one circuit to another circuit through a magnetic field, as shown here, right, there can be voltage surges in this circuit, right, or in the nearby wire. So these voltage surges does not make any physical damages as such, like previous cases, but it will malfunction the functionality of the control devices without a reason, right? There can be communication issues, there can be unexpected alarms in the system, there can be issues in the relay logics. So operation can be interrupted due to this magnetic and inductive coupling surge or transient voltages, right? So due to this inductive coupling, we can see mostly noises in the power system. These noises in the power system mostly happen due to this magnetic and inductive coupling. And the third reason what we discuss is electrical static discharge. Electrical static discharge happens when we use electrical appliances, electrical components for a longer period over a time. There can be electrical charge stored in certain components, and this electrical charge can be discharged to the earth wire or nearest conductive part. At that time, there can be electrical voltage surges. So that's how static discharge contribute for electrical surges, voltage surges in the electrical system. Then external sources, right? External source, first one is direct light. Lightning strikes are most common source of extreme transient overvoltages, right? So this is the waveform of a direct lightning strike. This is the current waveform of the direct lightning strike. So when there is a direct lightning, so this is the test impulsive voltage waveform, current waveform, right? Suddenly current increase to the 100% level within 10 microseconds, and suddenly come down to 50% level within 350 microseconds. So this is the duration of the transient period, right? 350 microseconds. Therefore, we call this direct lightning current waveform as 10 by 350 microsecond wave, right? This has a very high energy, and this is the worst case of transient voltages, right? So then the next one is indirect lightning, right? Indirect lightning means lightning can strike to a external line or something which is connected to the building, and high power of electricity can transfer through the line to the building, right? So in that indirect current waveform shape is like this. It reached to its maximum level within 8 microseconds, and duration of this wave is 20 microseconds. Therefore, it called as 8 by 20 microsecond current wave, right? Which has a low energy compared to the direct lightning, and it can occur very frequently in the electrical system. So sometimes even without we are having here any notice of thundering or lightning situation, there can be surges coming into the building due to this indirect effect, which lightning happens maybe 1 kilometer, 2 kilometers away to our current place, right? So these waves, this high power energy can transfer to our electrical system through the lines. So then this is the transient voltage waveform due to indirect light, right? So this wave is reached to its maximum within 1.2 microsecond, and duration of the wave is 50 microseconds. So therefore it's called 1.2 by 50 microsecond test impulsive voltage waveform. So now we know, we have an idea what are the external sources and what are the internal sources which cause for transient voltages. Let's move on. Now let's look at a comparison of these different types of voltages, right? Transient voltages. Now, in healthy case, our waveform is something like this. It's smooth sinusoidal waveform, and there can be dips in the waveform due to certain reasons. But this voltage dip doesn't cause for any serious damages, right? Voltage drops suddenly and come back to the normal level. And also there can be ripples in the voltage waveform in this area, right? Those ripples, those are not spikes, but ripples. The reason for this is harmonics, right? Harmonics, when we have harmonics in the electrical system, harmonic distort the voltage waveform as well as the current waveform. So due to this voltage waveform distortion, current also get distorted. So, but these are harmful, not very dangerous like spikes. These distortions also has adverse effect like overheating in the element, but not dangerous like spikes, right? So then surges. There can be small surges in the system, right? Transient surges. So, which also cause not very high, considerably high spikes in the voltage waveform. And you can see here number 4, switching surges. Right? Switching surges are considerably high. It goes up to kilovolt level, right? Kilovolt level, switching surges. Then the 5th one, as shown in the graph, those are lightning surges, direct and indirect. Those are very high compared to all other reasons, right? So now you can see here in this graph, switching surges and lightning surges are the most critical voltage surges or voltage spikes happen in the electrical system. Therefore, we need a mechanism or we need a device to protect our electrical system in this region, right? This region, of course, not very serious, no really high impact, but in this region, definitely we need a device to reduce the or bring down to non-hazardous level, as I explained earlier, to keep our system reliability and equipment healthiness safety, right? Therefore, we need surge protection device, right, to limit the surges happen in this area, right? So then let's move on. So then now we know what are the reasons behind this voltage spike, right? So then let's try to understand what are the standards applicable for this transient voltage and surge protection device, right? So we commonly use in our building applications, electrical installations, IET regulation, right? So the latest version is we use for our electrical designs is 18th edition from 2018, right? So in this under section 443 means in chapter 4, section 4, section 443, it says protection against overvoltage of atmospheric origin or due to switching, right? What it says, this section deals with the protection of electrical installation against transient voltages system and against switching or voltage generated by the equipment within the installation, right? So standard stress, there can be surges within the system, as I explained you, internal sources and atmospheric origin at the external as external sources, right? And also it stressed that protection against transient voltage shall be provided because of these consequences can be happen to the electrical system, right? So IET regulation force us to use a protection device in our system because of these reasons, right? Result in serious injury to or loss of human life. So it says there can be injury or loss of human life due to this transient voltage surges, right? And also interruption of public service. As explained in the introduction also, there can be interruptions to the services. So, and also it can damage the cultural heritage, right? then results in interruption in commercial and industrial activities, right? So our activities can be interrupted. Therefore, we need to have a proper surge protection mechanism to eliminate. So in this section, it stresses us, highlight us, you need to have something to protect your electrical components, right? And also in the same section, in 18th edition, it says how you select it. It tells us, it explains us, you can't do it in ad hoc manner, do a risk assessment, and determine whether transient over voltage of atmospheric origin is required or not, right? We don't need to provide surge protection for every electrical installation, right? It's a cost end of the day, right? It affects the investment, right? So as a designer, we need to do a proper evaluation and see whether we need it. Otherwise, if you are working as a consultant or engineer in a project, our investor will have to spend money on this, right? How do you do the calculation? Calculate standard ask us to calculate the risk level, right? They ask us to find the CRL value and see whether you need this or not, right? So this is the equation given in the standard. CRL, calculator risk level, equals F environment divided by LP into NG. This F ENV environmental is an environmental factor. You have a table here. If you refer the standard, you can get this value, right? So then LP is a risk assessment length in kilometers. How many lanes? And this is also given in the standard. If you refer this section 443, right? Then NG is the lightning ground flash density per square kilometer. This is also given. There is a map. In that map, you can find out what is the value for this, right? So I'm not going to discuss and explain you how to apply this in the equation. So this is the equation. These are the parameters. If you refer this standard, you can get an idea how to calculate this. And then again, standard says if CRL is more than 1000, you don't need, not required. If it is less than 1000, you need a protection device. Transient voltage of atmospheric origin, right? What we need to protect against. So we need to find this out, and we need to see the result, whether it's less than 1000 or more than 1000, depending on that, we can decide, right? Actually, this is in the 17th editions as well. 17th edition also says, in 17 editions also mention, you do this and see whether you want this protection or not, right? And the next one is 534. In section 5, sorry, in part 5, in IT regulation, part 5 is a selection and erection of equipment. Under this part 5, chapter 3, 4, you can find a separate clause, separate section for device for protection against over voltage, right? There it is clearly mentioned. This was not in the 17th edition, right? 17th edition, it was blank, but in 18th edition, it is clearly given. So it says you have to follow these parts in your design, right? So it gives an introduction, then it guides us, gives us details how to select it, what are the types, what are the locations, how to connect it. Those things explain very clear, right? And one thing I want to explain you here, actually this IEEE regulation, IT regulation is an extracted version of BS 7671, right? Therefore, it doesn't cover the entire spectrum of electrical engineering installation details, right? Technical details. Therefore, always this IT refers other British standards. So for this overvoltage protection and selection of SPDs, it refers these three standards as well. It gets information from these three standards: BSEN 606641 and BSEN 62305 series 1 to 4. This is about lightning protection, surge protection, and those things, direct, indirect lightning. And BSEN 61643, right? It refers these standards also to get the information into this. Actually, now these areas we can discuss down the line, right? Now, you need to understand, you need to get an idea. The surge protection design is clearly defined in the IET regulation, where it was not in the previous edition, in 17th edition, right? It's a new addition, one of the addition in the 18th edition, right? Then let's look at what are the different technologies we use for surge protection devices. I told you we need a surge protection device bring down the voltage level to a non-hazardous level in the electrical system, right? And I explain you the hazardous voltage level in the electrical system is not a constant throughout, right? So it's changed from one place to another place. So then surge protection technology is also different. There are different technologies we use, and therefore we have different types of surge protection devices, and we need to understand, we need to know what technology of surge protection device we need for this particular place in the electrical installation, right? So that is part of the selection of surge protection device. Before that, we need to know what are the technologies, right? First technology is transient spark gap, TSG type surge protection device, right? It diverts high surge current harmlessly to the ground and limit the overvoltage to acceptable level. Actually, this we use for direct lightning surge protection devices, right? Transient spark gap type voltage surge protection devices we use for the direct lightning surges. So you can see here, right? It's like this. So there is a air gap, and there is a triggering needle also. So this is the internal construction of this particular SPD surge protection device, right? So then the next technology used is metal oxide varistors, MOV type, right? We have TSG type, then we have MOV type. So MOV type is the type we use very commonly in our normal AC voltage surge protection application. It's an nonlinear device. Non-ohmic current voltage characteristics are there. It's similar to a diode, right? It's similar to a diode. It starts conducting at a certain level, and it stops conducting beyond that level. It's at like a diode. Current pass through only one direction, right? It's like this. Then the third type, gas discharge tube. In gas discharge tube, we mostly use in electronic circuits, right? Within the circuit, inside the circuit, you can see this gas discharge type surge protection device. used to protect the electronic equipment. Mostly we use this gas discharge tube, right? It has a fast response time, low capacitance, and longer lifetime also. It can handle high surges as well, right? But it has a very low discharge capacity. So these are the three different technologies we use nowadays for surge protection as SPDs in our SPDs, right? So then let's try to see what are the different types of surge protectors are available, right? We have three types of actually surge protection devices. Devices are divided into three types. First one is type 1 surge protection devices. Second one is type 2. Third one is type 3, right? We use these different types in different places. Let's try to discuss later, right? Down the line. So type 1, we use to protect against direct light. So we used to protect this current wave, right? Type 2, normally we use to protect against indirect, right? Type 1 for surge current, type 2 for surge indirect, right? So this is the waveform that we need to handle, right? Then type 3, we use for same this one, right? Goes overvolt switching type of over voltages, right? Type 3 we use. So try to remember that there are three types: type 1, type 2, type 3. Type 3 has this characteristic, right? Test impulse voltage. Type 2 has test impulse wave 8/20, and type 3 also same 8/20. The voltage impulse wave is 1.2/50, right? So then let's look at how we use these different types and where to use it. Right? So before we go into the selection, we need to identify what are the lightning protection zones we have, right? Based on the lightning protection zones only, we decide what type of a surge protection device we need to use in our installation, right? So now in this figure, you can see different types of lightning protection zones, right? Zone LPZ 0A. Right? Zone LPZ 0A. This area, right? This area. This area. Unprotected zone. It is not protected against direct lightning, right? We have a lightning protection system for this particular building, but the shaded area in red color is not protected by the lightning protection system provided, right? So then there can be direct lightning and also no shield, no protection against lightning electromagnetic interferences, LME, right? There is no protection. If there is a direct lightning which can hit whatever the equipment or whatever the structure in this area. And also if there is a lightning nearby, there can be induced voltages because no shield against lightning electromagnetic interference, right? Then zone 0B. Zone 0B means, let's try to color in a different, this area, still outside the building, but that area is covered by the lightning protection system, right? Now if you use rolling spear method to determine the lightning protection system, it will be like this, right? So then you know that the touching points are vulnerable, unprotected. Below the touching points, this area is protected by the lightning protection system. So this zone is protected, but there is no shield against LEA. Means lightning, electromagnetic interference pulses is not shielded in this area, right? If there is a lightning nearby, the interferences can be happen in the equipment or whatever in this area also, right? So then we have another zone, LPZ1, zone 1, which is inside the building. Therefore, it is covered by the direct lightning, right? It is covered by the direct lightning, but it is not fully secured by the induce, right? If there is a lightning somewhere here, right, the voltage can induce inside as well, right? It is not fully covered against LEN, right? Then zone 2, a place like this within the installation, right, which is covered by the lightning protection, which is covered against lightning protection, as well as very low impact due to induced voltages, right? Means very low impact against the electromagnetic interferences. If you take a zone or cubicle or something like this in this area, which has a metal housing or something, in that area, it is obviously protected against the direct lightning, as well as no LEME interferences in this area, right? So now try to understand these different zones and why and how we have categorized these zones based on the structure of the lightning protection system against the building partitioning and building element, right? So I will explain you further this in my next slide. So then you will understand more what is the lightning protection zones and how it is categorized, right? So now in this figure also same like before, right? But here I want to highlight you another thing. So it's same like now this area, zone 0A, right? And this area where the lightning protection is there but not protected against the LEMP, zone 0B, right? Then this is zone 1, protected against direct but not against LEMP, right? Now you can see here this area also similar to this area, right? If you look at the nature of the building, right? In construction point of view, this area and this area has the same, right? One floor below, but no much difference. Only difference is there are equipotential bondings here, right? So due to this equipotential bondings, if there is a interference, electromagnetic interference, it can be discharged. Therefore, this particular zone is more secured than this zone, right? So that's why this is zone 1, this is zone 2, right? It is more secured, right? So now you see this zone is 3, zone 3. Here and here almost same, but here you have equipotential bonding, right? And it is more covered, therefore it is zone 3. So that's how we do the survey. Not just look at the building orientation and building partitioning. You have to study how these equipotential bondings are there, how this lightning protection system conductors are installed in this building. By looking at the whole picture, bigger picture, and overall aspect of the lightning protection, only we can decide, right? So that's why I show you this as well, right? In the first one, it's very simple, right? In the first one, it's very simple. Just you have 1, 2, 3, 4, 5, 6 zones. But here you can understand it's not straightforward like I explained in the previous one. We need to further study the lightning protection system conductors pass through the building to decide what is the lightning protection zone, right? So then let's move on. So now let's look at, now I explained you before, we have 3 types of surge protection devices: class 1 or type 1, type 2 or class 2, and type 3 or class 3. Then let's try to understand few special characteristic of these different types of surge protection devices, right? Type 1 surge protection devices are mostly used at the entry of the building. We use at the entry of the building, right? So that means we use class 1 in the main distribution board, right? We have the main distribution board at the entry of the building, right? So this device we use to protect against the direct lightning strike. Therefore, this is the current value, right? And also this is the test impulse wave type, right? And here it says it should be below 4,000. I'm not going to explain you this now. I will explain you this below. I have another slide to explain what is this voltage level, right? So then understand that, remember that we install this class 1 lightning protection devices between zone 0B to zone 1, right? That means from protected area to building inside. If we have a electrical panel or something, mostly the MSB, we use this class 1 type surge protection device, right? Then we have class 2 type surge protection devices. Class 2 type surge protection devices we use further inside in the electrical system, that is in the sub-distribution boards, right? So let's move on. So class 2 type surge protection devices we use to protect against indirect light, right? Indirect light. So the wave or pulse shape is this 8/20, right? And typically 20 kilovolts. This also I will explain. And type 2 surge protection devices we need to install in a way which does not affect the other protection devices. So this also I will explain later why we need to use it before the RCDs, right? So remember for the moment, class 2 or type 2 SPDs we use in between zone 1 and zone 2. So between zone 1 and zone 2, mostly we have SDBs, sub-distribution board. Therefore, inside the sub-distribution board, we use type 2 SPDs, right? Then we have type 3 SPDs. Type 3 SPDs mostly we use at the terminal end of the equipment at the final level. So type 3 we use in the zone 3. Right? So we use between zone 2 and zone 3. So the pulse shape is this one. And voltage level and current is this. And protection level, it should be below 1500 volt. This also I will explain you later, right, with another graph. So then let's try to understand now some technical characteristic of SPDs. Actually, this is very important. When you are going to select a SPD for your application, you need to do a proper evaluation on this. If you are asked to compare 2-3 proposals for the same project, so you need to know what are these parameters, right? First one is maximum continuous operating voltage, right? So surge protection device we install in the electrical system. So what is maximum continuous operating voltage, or UC, means that is the RMS voltage value applies across the terminal of the RCC, so a surge protection device, right? So in our system, our RMS value across the terminal in one phase is 230, right? But we use here 10% safety margin for the surge protection device, then it comes 253 volts. So therefore, UC value of the surge protection device, what we used here in our system, should be 253 volts, right? Then lightning impulse current, IMP. Lightning impulse current, this is the wave shape, and this mostly we need for type 1 surge protection devices, because type 1 surge protection device are the devices we use for lightning impulse protection, right? Then this is the wave shape, right? It is class 1 type, and the current level is 100 kiloampere for 3 phase, and for single phase it is 25, right? And this value also depends on the type of lightning protection class, not the surge protection class, right? We have 4 type of lightning protection classes, 1, 2, 3, 4. If it is class 1, 100 kiloampere, but if it is class 3, 2, 3, 4, then this value also less, right? So if your lightning protection class is 1, means high risk lightning protection class, then you need to use your surge protection device kiloampere level as 25 per phase, right? Then nominal discharge current, IA, right? Nominal discharge current mostly apply for the type 2 type SPDs. That is the current flow through the SPD, right? Now here in this graph, you can see this is the IN, right? This is the maximum safe current can be flow through this SPD. In certain products, they are talking about Imax as well, right? Imax is the maximum current, but in mostly we use IN, that is the maximum safe current which can pass through the surge protection device, right? So when you decide this current, you need to consider this also given in this table, right? So you need to look at the building environment as well to decide what is the IN value, right? So if the building is located in an urban area, so there are so many other buildings, so chance of a direct lightning is also very less. Therefore, this value is less. building is located in a plain area, so chances, again, probability is high. Therefore, we go for higher value, right? So if it is supported by other structures, I mean, risk is supported by other structures like trees and other things, right? Ponds, etc. So then we take it as 65, right? So depending on this condition, you need to select what is the Ka level of type 2 surge protection device, or what is the IN value, right? So then let's move on. So then let's look at what are the other technical parameters we have. Then voltage protection level, UP. Voltage protection level means instantaneous value on the terminal of the SPD, right? Now here in this value, this is the voltage level, which I talked about earlier, 4,000, 5,000, whatever. So I will explain further this one, right? Then residual voltage, right? Residual voltage is a peak value, operates between the terminal of the SPDs due to passage of the discharge. When discharge current goes through, at that time voltage is the residual voltage. Then temporary over voltage value. So when these surge protectors are connected into the system, there can be a temporary over voltage. So surge protection device, when it is not in operation, when it is in standalone condition, it should be able to withstand this temporary over voltage values, right? So this also given in the surge protection device. Then voltage withstand level, right? What is the insulation level corresponding to the surge protection devices denoted by voltage withstand level. So then let's look at what is impulse withstand voltage or basic insulation level. If you take, as I explained earlier, electrical component from the start point to the end point of the electrical system, we can divide this equipment into 4 categories. First one is category 1 equipment, right? Category 1 equipment are the equipment you can find down the line of the electrical system, right? Electronic circuits, computers, those kind of things. In this graph, this region, right? So the insulation level, maximum voltage that can handle this equipment is 1.5 kiloampere, very low. Then category 2, household appliances and other stuffs, which is further above the system compared to the region 4. It has a higher level, 2.5, right? Then region category 3, like distribution board, circuit breakers, those things, it can withstand for 4 kilovolt. It is in this region, right? Region 2. Then region 1, electrical meters and primary circuit protection devices and other things. So which connects with the external system, right? Which has a very high insulation level, right? So now when you install surge protection devices, you can see here, type 1 surge protection devices are installed at the entry point. Then at the SPDs, type 2 devices. Then final terminal equipment, type 3 devices, right? So then your type 1 SPD should be able to handle this 6 kilovolt voltage level. It should not increase. It should not let go up the voltage level beyond this one. Therefore, the voltage level value of the surge protection device, that means UP should be less than 6. kilovolt in this type of surge protection device. Type 2, it should be less than 1.5, right? Because if it goes more than this, it can be harmful. And type 3 also 1.5. If it goes more than that, it will damage the insulation level, insulation of the equipment, right? So that's how you select insulation level of the surge protection device. So then let's look at how we install. Now you know what are the technical parameters, right? So these are the important technical parameters: maximum continuous operating voltage, lighting impulse current, nominal discharge current, right? Then voltage protection level, UP is this one, right? So that's what we discussed just before, right? Then residual voltage level, temporary voltage, then voltage withstanding. These parameters are given with the surge protection device. So we need to do a proper evaluation of these parameters before we select the device, right? Then let's look at how we install a surge protection device for a TT system. Now you know that earthing system, we have TT system, we have TN system, TN divided into two other systems, TNC, TNS, and IT system, right? In different systems, the installation of SPD is not similar. In TT system, we install it like this. We install surge protectors in each phase. Then after that, between the neutral and earth point. This is the correct way of installing surge protection device. And also, when you install type 2 surge protection devices, we install surge protection device above the RCC. Otherwise, if there is a fault in the surge protection device, there can be nuisance strippings in the RCCB also, right? When the surge protection device divert the surge, if we install it above the surge protection device, RCD will take it as a residual current difference, right? It will appear on the RCCB as a current difference, and then at the time surge protection device protect the surge, your RCCB also will be tripped. So it is not a good thing. Therefore, we need to install type 2 surge protectors above the RCCBs, right? This is the correct way of installing SPDs in TT system. Now TT system, here you can see we install type 1 at this point, at the entry point, then type 2 at the SDB level, and type 3 at the terminal level, right? All three levels we can install SPDs as shown in the diagram, right? Then again, further, if I elaborate that, so entry point, type 1, this is how we install it, every phase, then neutral and earth, right? Then type 2 and type 3, right? Type 1, look after lightning impulse. Type 2 and 3, look after switching surges, indirect voltage surges, right? Then, just for your information, how to install SPDs in other systems, right? Other earthing systems. Actually, we don't have commonly here in other systems, rather than it's a special type of an installation, right? So this is how we install SPDs in TNC system, right? Only 3 SPDs between the phases, right? There is no SPD in the pen conductor, right? Then TNS system, we need 4 between the 3 phases plus between the neutral. and we common with the protective earthing and connect it to the earth terminal, right? Then IT system also similar to TNS system. There we install 4 surge protectors between 3 phases and neutral and earth common PE point. Then PE point we connect to the earth terminal, right? So here in this table you can see in TT system phase to neutral, it's recommend if you want you can install, but it is mandatory to use phase to earth plus neutral to earth, right? TNS system only phase to earth, and TNC system recommend to install phase to neutral, but mandatory to install phase to earth and neutral to earth, right? And TT system also phase to earth plus neutral to earth, it is mandatory to install, right? So then let's look at what is the correct connection of cable in the SPDs, right? So connection of SPDs to load should be as short as possible to reduce the UP value, right? Now here in this diagram, you can see this is the UP, right? UP is the voltage across the terminal. I explained you before. But if you use, we normally install surge protection device parallel to the load, right? This is the earth terminal, load also connected to the earth, and we install between earth and live conductor, right? So if we use a longer cable means this part, and this part, right? This UP doesn't, the required UP doesn't apply across the SPD. So therefore, the required protection value we can't get if we increase the cable length, right? Our terminal load has a certain insulation level. If we increase this, then this part also added into this, and then it exceeds the value here. Therefore, we need to limit it. It says less than 50 centimeters, means half a meter, right? You should connect surge protector within 50 centimeters to the earth terminal and live conductor. Otherwise, your protection will not be effective, right? Then according to the IEC 60364, for type 1 SPDs, the cable size should be 16. Type 2, you can use 4 millimeter square copper. If it is copper, 4. If it is copper, 16 for type 1, right? So this is a very important point, your cable length. If you exceed the cable length, you will not get the effective protection level against you. Your UP will be affected, right? So then let's look at the installation methods of SPD. Now we are coming to the end of the presentation. So I have only few more slides, maybe maximum 5-10 minutes. And when we install SPD, if it is a metal PVC enclosure, so this is the best way to install, right? PVC enclosure doesn't conduct, so therefore you need an additional earth terminal near the surge protection device to reduce the cable length, right? If it is metal enclosure, you can install it this way. First, circuit breaker to give the overload protection to the SPD, then after below that you can install SPD, then you can connect it to this earth terminal, right? Then so these are also correct installation practices. Somehow what we need to achieve is to reduce the length of the cable from live terminal to the earth terminal, right? Then there are 5 rules when you do a proper SPD installation, right? First one is that comply with the length of the STB connection between the network via SPD, and the length of the terminal block should not be exceed 50. We discussed this already, right? So this is the best practice when you install it. So now here in this case, the SPD and the overload protective device, circuit protective device is a separate one, right? Separate circuit protective device and SPD. And there are certain SPDs, it comes as an integrated unit, SPD and circuit protective device. In that case, you can install it like this, right? Here it is separated, but always try to minimize the cable length, and maximum allowable is 50 centimeters. And second rule, your power incoming line and protection feeders should be separate out, right? So why it should be separated out? One side is polluted, other side is clean. Therefore, cable should not be mixed inside. If it mixes inside, it will affect the protection as well. Then third rule, incoming feeder phase, neutral and PE conductor should run one beside another in order to reduce the loop surface, right? So rule number 4, the incoming conductors of the SPD should be remote from the protected outgoing conductor and avoid polluting them by coupling, right? It should be separated, incoming side and outgoing side, right? So then the rule number 5 also describes how we should properly connect it. Now in this figure, in this diagram, you can see what is the best practice of use surge protection inside the panel board, right? Here it mixing. Here it mixing cable, but here it doesn't, right? It's one side, one after the other, it's clean. So when you install or when you inspect an installation, you need to look at these points, right? If it mixed like this, it might be affected for the final result of using this SPDs. So then lastly, what I want to highlight, now we gone through certain installation aspects and certain theoretical aspects of using SPDs, right? So when you are designing a surge protection system, there is no any hard and fast rule, right? You need to consider the site condition. You need to study the site condition. When you study the site condition, you need to look at what is the type of earthing system, what is the nature of the earthing system that we use, right? And also it is very much essential to study the lightning protection system in the building and how this lightning protection system conductors run inside the building to understand the lightning protection zones, right? So then the nature of the electrical, whether we need to protect this equipment or not needed to protect this equipment, has to be evaluated properly and studied properly. After study all these conditions, then we can decide at which place we need SPD and what is the type of SPD and what are the technical parameters of the SPDs that we should use, right? Then with this note, actually surge protection is highly site specific process, right? We need to study the site condition before we decide what is the type of SPD and where to put the SPD, right? With this note, I am going to I have come to end of my presentation. So then I will hand over the forum to the moderator to
Thank you.
check whether we have questions regarding this, what I have done.
Thank you very much, Engineer Pedu. Good evening, ladies and gentlemen. This is Dilan Tilanga from Building Services Engineering Sectional Committee. So, since the topic is much sensitive for general public as well, so we are getting very number of questions. So, I'm shooting one by one. Since the time is running out, limiting my words as much as possible. Right. Our first question is,
Yes.
what is the difference between lightning arrestor, surge arrestor, and SPD?
Actually, lighting arrestor means we have two different systems here. One is lightning protection system, and other one is surge protection system. Lightning protection system we use to protect the external structure of the building, right? For that we use lightning arresters. Surge protect lightning arresters we use to protect from the indirect, from the direct lightning. Okay? Surge protection we use to protect our electrical components from indirect lightning. So lightning arresters for direct lightning, surge protection for indirect lightning.
Thank you, Engineer Pedu. For the next question, actually, this question came in different forms. I'll take the first one and get the added part for next questions. The question is it necessary to keep a fuse or MCB in between the bus bar and the SPD of a main switchboard?
So sorry, I couldn't hear you properly. MCB.
Is it necessary to keep a fuse or MCB in between phase bus bars and the SPD?
Yes. Actually, we need to have a overcurrent protection for the and also short circuit protection for the SPD. Right now, suppose that when there is no lightning and when the system is in healthy condition, right? If there is a short circuit happen in the circuit before the SPD installed in the circuit, right? Upstream of the SPD, what will happen? SPD will be damaged. Therefore, we need a overcurrent protection device as well as surge protection device, as well as short circuit protection. That means circuit breaker, MCB, MCCB, or fuse to protect the surge protection device. Yes, it's a must actually. So the required MCB capacity will be given by the surge protection device manufacturer. He will say what is the capacity of the MCB, whether it's 60 ampere or 100 ampere, whatever, will define. And the short circuit level, we have to study the short circuit level of the system, and we have to calculate what is the short circuit level of the electrical system at the point where we are going to install the SPD. Based on that, we can select what is the overcurrent value and what is the short circuit value that we are going to use to protect the SPD.
Right. Engineer Petum, next question also related to that one. This person is accepting that it's necessary to have this MCB or HRC fuse for this application.
Yes.
He said these devices cannot withstand 6 kilovolt or impulse withstand voltage. So what is the way to connect SPDs to the system in that case?
So so actually now I explain you Yes, July. Actually, now here in this graph, at the entry point, insulation level is 6 kV, right? 6 kV. So the surge protection device that we are going to install at this point definitely should be less than 6K. Otherwise, it won't protect the equipment, because the equipment in this area, this region, is rated as 6K. So normally 6K we have at the entry point. So at the entry point, we use type 1 SPDs, right? So type 1 SPD, when you are selecting a type 1 SPD, you need to look at what is the UP value. What is the UP value, right, of this? If it is more than 6, then no point of using this SPD. It should be definitely less than 6K. If you can select 5K, 4K, or whatever less than this, is the best for protect 6Ka insulation level of equipment. 6K insulation level of equipment we can find at the entry point of the installation. So that means 6Ka UP value you will have in the type 1 SPDs.
Thank you, Engineer Petu. Next one. Although SPDs are used to limit transient over voltages,
Yeah.
SPD ratings are coming in kiloamperes of current ratings. Why is that?
SPDs, can you please repeat it again?
Yeah, although SPDs are used to limit transient over voltages,
Yeah.
SPD ratings are coming in current ratings. Why is that?
Yeah, when there is a transient voltage, when there is a high voltage spike, the same time there can be high current as well, right? So therefore, your SPD should be able to handle both, not only one, right? When a transient voltage happen, now example, direct light. When there is a direct lightning, right? Your voltage level is 6,000 or whatever, right? At the same time, discharge current through the line is kiloampere. Therefore, when you select SPD, you need to look at both. So that's why you need to find out what is the correct current kiloampere level for the particular SPD. Especially this one we need for type 2 SPDs, right? In type 2 SPDs, I explain you that. Yeah, in type 2 SPDs, there is a nominal discharge current as well, because current discharge through this, right? Now here look at, depending on the building environment, whether it's 20 or 40 or 65, we need to decide, and we need to select the Ka value suitable for this application, this site condition as well, because this current discharge through this. That's why Ka level also important.
Right. Thank you, Engineer Petu. Next one. Once a surge go through SPD, should we have to replace?
Do we have a?
Should we have to replace that? The second part, if not,
Yeah.
if there are any limitation to number of surges that the device can withstand.
Yes, actually, certain surge protectors has discharge counter, right? We can see how many times the surges has discharged through this, and the this product sub manufacturer recommend how many times we can use this and what is the lifetime for how many discharges this can withstand. Actually, for that, yes, there is a limit, but it's not one. So if there are no physical damages, we can use it, but it's depend on the product manufacturer's recommendation. It varies from product to product. You need to refer the catalog and decide on this. Sometimes in certain SPDs, I have seen there are color patches, color marks. It changes the color and it indicates, okay, now you have to replace the SPDs. Yes, when there are more discharge, the lifetime also goes down.
Right. I think that's well answered. I think then the next one, if you are using lightning protection to a building,
Yeah.
Is there any compulsory requirement defined in the standards to keep class 1 SPDs in the electrical system?
When we are designing a lightning protection system, actually designing of the lightning protection system and the surge protection is different. When you designing a lightning protection system, you need to calculate the risk level and you need to decide what is the class of the lightning protection that you need, right? But surge protectors, it's a compulsory to install surge protection devices. It was not in the 17th edition, but it is explained as a mandatory requirement in the 18th edition, IET. So we have to install, right? So we have to install at different levels. And we have 3 types of SPDs, type 1, type 2, type 3. So at the entry point, we normally we have to install type 1 SPDs. Type 1 SPDs mostly look after lighting discharge currents. Okay. Then type 2 SPDs, we install SDB level, type 1 MDB level, type 2 SDB level, type 2 indirect lightning and switching surges. So based on that only we decide what is the type of SPD and what is the class and what are the technical parameters. We need to install lightning protection system as well as surge protection system. Right? So I explain you, we have several type of zones. So based on this zoning, we have to decide what is the lightning surge protector, correct type of surge protector we need in our installation. Right? If we don't have a lightning protection system, then definitely we need type 1 surge protection protectors everywhere. We need to evaluate it, actually. We need to evaluate it, but if there is no lightning protection system in the building, right? So what will happen? So then everywhere will be like zone 0B. So then everywhere we have to install type 1.
Okay, thank you, Engineer Patu. The next one, what are the ways to inspect whether my SPD is working properly?
SPD is actually you can't test at site mostly. To check the SPD, you need to test it with the impulse tester. Impulse, you need to give the correct impulse wave and you need to check whether it's working, but we don't have such type of sophisticated test equipment normally at site level. So you need to take the SPD to a laboratory or SPD manufacturer who are having this special type of tools and needs to get it tested. If you want to test it at site, then you need to take those sophisticated equipment to the site level and need to check it, but it's very difficult to bring those type of things. Physical evaluation you can do by looking at this and checking the number of tripping and other things and number of surge discharge and other things. But if you want to check the performance, you have to get it to a testing laboratory.
Right. Right, Engineer, thank you. Then next one, I think you have answered some of the parts of this question, but anyway, I'm asking the same one. What are the external factors that a SPD can get damages?
External factors. So when there is a external factors,
I'm thinking. This is something like the same one you answered before, the short circuit and other things. We are placing some MCB.
Yeah. So actually, SPD's external factors means SPD can be damaged due to short circuit. It can be damaged due to overcurrent, and also there can be physical damages as well. No? So that's why we normally install SPD inside the enclosure. So other than that, there are no any other external factors which an SPD can damage. SPD is like MCB or RCCB, right? So if surge current pass through which is not handled by the SPD, then definitely it will damage, right? So it happens if you select a incorrect SPD. Other than that, other two factors and physical damages only. So what we can see at site levels.
Right. The next one, is there any lightning ground flash density map for Sri Lanka?
Actually, I haven't seen for Sri Lanka, but we have a world map. We have a world map ground flash density. They are actually I don't have right now to show you. So there you can see Sri Lanka also as a one whole whole country as a one region. There you will see it's a colored map. So depending on the color, you can find out how many lightning strike per year per square kilometer. So country part by part we don't have, but meteorological department you can find certain details. One time I also tried to get it, but it's difficult here. We don't have records, and in international publication, Sri Lanka is not recognized in that way, different part-wise, because it's a small country. So I think they have considered it as a one region.
Yeah, well understood. The next one, is there any local code to follow for lightning and surge protection?
Local code.
Yeah.
Actually, here in our designs, in building designs, in building service applications, we mostly use for electrical designs IET regulation, right? So that is the standard we use in our design. So though it's not a local regulation, but for all our designs we use IET, and also whatever the related international standard we can use. But for local standard, we don't have any local standard according to my knowledge, which specify lightning protection and surge protection into this depth. If you want to design a system to depth what we discuss now, you have to definitely follow an international standard, not a local standard.
Right. The next one, actually this one already answered in the lecture itself, but the second part I think is important. The question is, Engineer Badam, is it okay to connect SPDs to common earth bar of a distribution board? I think you explained that in the lecture,
Yeah.
right?
Yeah.
Yeah.
So here our challenge is, as I explained, to reduce the cable length, right? So definitely we have to connect it to the distribution board earth, because otherwise, if you run the earth wire, the cable directly coming out from the SPD to a external earth terminal or something, then the cable loop length will be high. So then it exceeds the 50 centimeter limit. So then it affects the UP value. So then the required protection requirement will not be met if you extend it up to another terminal.
But Engineer Badam, the next part of the question is at actually the length, but the length from distribution board to earth pit. Is that the same length that you were discussing about?
No, not from the, so that is impossible. No, 50
Yeah.
centimeter. This is from SPD to the immediate earth terminal. From there to earth pit, definitely you can, because we size the earth cable accordingly. Right now, I explained in the presentation. If it is type 1, we use 16. If it is type 2, 4 millimeters also enough. Right. So this cable should be less than 50. The rest of the earthing system we decide on the other factors, short circuit, the current and other things, right? Take into consideration other electrical design aspects as well. Based on that only we decide. So this part only we need to limit to 50 centimeters.
Right. Okay. The next one, how to protect devices from continuous high voltage supply. Nowadays, it's very common problem due to bright sunlight time due to rooftop solar system. Will surge devices work for that?
So repeat the question again, please.
Yeah, how to protect devices from continuous high voltage supply. Nowadays, it's very common problem during bright sunlight time due to rooftop solar system. Will surge protect devices work for that?
No. Due to direct sunlight, over voltage can't happen due to direct sunlight. There is no any. What I understood in that question is asking whether the direct sunlight affect for over voltage, right? Is that?
Yeah, kind of like that. It's kind of confusing question.
But there is no any relation between the the temperature and the over voltage. Now, when you do a cable selection, obviously you need to take into consideration the ambient temperature, right? So then based on that only we do the cable selection. So once you select a cable based on the ambient temperature, again direct sunlight into this, there is no, but we discussed what are the reasons that transient voltages can happen. There are internal sources, external sources. Internal sources, switching, right? Magnetic coupling, static discharge. External, direct lightning, indirect lightning. Those are the reasons. So there are no any other, environmental factors like this impact very much into transient over voltages.
Right. Next one, Engineer Badam. Is it essential to install a type 1 SPD in the main electrical panel where incoming cables come from the transformer is connected?
Continue.
Yeah, or just type 2 SPD is enough?
No. Transformer is not an issue for us in this case. Actually, yes. If there is a lightning strike to the transmission line, it won't pass through the transformer. That's right. But normally for the entry point, we need to install, then in between, I explain, in the there can be lightning interferences as well, right? So no need to, now transform is bit far. If it is inside, then yes, then even type 2 is enough. But if transform is outside, then there is again a cable part, right? So there can be induced voltages. Therefore, it's better to install. You need to, it's I explained, it's a highly site specific design. So you need to look at how it is installed and whether there is any chance of transferring direct lightning into the building. If there is no chance of direct lightning into the building, so then you don't need to use type 1. Type 1 we mostly use to protect from the direct lightning, right? So for the incoming line, there is a high chance of transferring direct lightning into this depending on the site condition. But if you are very sure about that there is no chance of direct lightning coming into this, then even type 2 is enough. That is for the indirect and switching.
Right. The next one, if we have a sub-distribution code going outside, such as external lighting, what type of SPD should be used in such DB?
So then you have to go for type 1. Because it doesn't matter, it's connected to the building inside, but then again, there is a high chance of direct lightning hit into the cable and transfer it to the panel, right? So in that case, type 1 is the best, I think, if you need a proper good protection.
Right. Okay, the next one, what is the recommended value for continuous voltages? Sometimes it might exceed 253 volt because of the movement of neutral point in the star system due to short circuit.
Yes. Yes. Actually, most of the surge protection devices are rated for this value. So if you can, because I also have not seen UT above this value, but if products available, that's better to use more than that. But if this is the value, then if such a thing happen, sometimes there can be damages to the SP. But as is standard practice, this is the value normally given with most of the SPD products available in the market.
All right. Those are the only questions came through chat box. Can we allow 1 or 2 questions if you don't mind, as live questions?
Yeah, not an issue, but I don't know the time, and if you can limit it to certain numbers, yes.
Of course, we can allow only 1 or 2 questions. More than that,
yeah, no problem.
Okay, thank you, Engineer Vedum. Ladies and gentlemen, if you have any questions, you can raise your hands and we can allow to unmute your mic then. We'll take 2 questions.
So no question means I think I have answered all of their questions, maybe. No?
I think you have answered all the questions. That's our
Yeah.
understanding, of course.
Yes. Yeah.
So, ladies and gentlemen, if you don't have questions, shall we move to the conclusion part? Yeah, I think we don't have questions. So we waited. And thank you, Engineer Pathum, and it's been a very good opportunity for me to have this discussion with you. And this is a very important topic regarding the vector. Other thing, as I have seen, we combinedly talk about lightning and surge protection, and most of the time, surge protection discussion get the minimum time. So this is a very important topic.
Yeah. That's true. That's true, because I'm also doing. I have other lecture notes, so every time in my other lecture notes also we have about 30-40 slides for lightning protection, then 2-3 slides only for surge protection. So I also spent some time to prepare this presentation, because I couldn't use straight away my other lecture notes, lecture presentation for this. So yes, that's correct. Actually, we always get very less chance to study on SPDs.
Exactly, yes. I think it's actually the first time we discuss about only about surge protection, considering the webinars that we did for around last 5 years. This is the first time we consider about this surge protective part. And thank you very much, Engineer Pathum, having this important time with us and sharing all the questions that we answered. And it's been very comfortable for me to handle this moderator as well. As the conclusion part, I think our team member Engineer Malaka is there for do the vote of thanks.
Hi, good evening, ladies and gentlemen. This is Malaka Samarratna from Building Services Engineering Sectional Committee, and let's move towards the final note of the day. We were attending to a really interesting lecture today with the participation of more than 140 members in the audience. Being engineers, we all should be well aware about the transient voltage protection and the use of different type of surge protection devices. To make our knowledge base wider, I'm pretty confident that the lecture today served us in a great way to enhance our knowledge in updated technologies. Moreover, it's been a great pleasure for us to join with Engineer Pathum Jayawardena, our resource person of the day, who was well updated on the subject. Dear sir, thank you very much for dedicating your valuable time for the benefit of this interested audience. This event wouldn't be a success if there wasn't an interactive audience like you all, raising your valuable questions and sharing the ideas you had help others to learn the content for further extent. Thank you very much everyone for the participation today. Finally, we would like to thank ISL staff for supporting us to complete the lecture successfully from the beginning to the delivery of the lecture. With that, we'll conclude the lecture today, and this will be our first webinar for the session 2021-2022. We'll come up with more lectures in forthcoming months as well, and we warmly invite all of you to be part of next lectures to come. Good night, everyone.